So a few years ago, I was experimenting with Neodymium Yag lasers, and these are basically lasers that can generate a pulse of 1064 nanometers using a flash lamp as a pump source. And the setup of the laser is essentially that at the ground state we have basically neodymium yag is a garnet crystal basically, and it contains basically states of atoms that have to be pumped using a pump laser or a flash lamp source at 808 nanometers, and there's a fast decay to an upper level and a relatively slower decay to a lower level. And essentially you can pump a laser with a flash lamp source or a diode laser source, and it will turn the input light into this 1064 nanometer output light, and this is a fairly bright light source. And this wavelength 1064 nanometers is quite useful for a lot of beam pumping in general. And one thing you can do with 1064 nanometers is you can do a thing called Q switching, which is basically narrowing the beam into a ultra short but high energy pulse. And this can create actually like a kilowatt or even megawatt laser power pump power, and it can actually cause ionization of the air. So actually this is a laser wavelength which is used very frequently in etching, but also in the field of medicine. It's actually the wavelength and type of laser that's used in tattoo removal quite frequently, but also skin and laser eye surgery as well. So it's a very interesting wavelength of light to explore, and primarily the setup that I had was a neodymium yag laser system with a basically a modified power control unit. This was actually a flash lamp driver that I was using to power the flash lamp, a xenon gas flash lamp, and it was incorporated in the laser structure in a kind of a reflective mirror structure, so it could radiate the crystal. Now the problem is that they're very power hungry devices, and typically they're used in like laser tattoo removal machines. This is actually where the casing of this came from, and it consumes a lot of power, but it does actually work. So this is a video I made a good few years ago. As you can tell by the camera, it looks like it was filmed with a potato by today's standards, but nevertheless you can actually see that the experiment that I was doing primarily was to generate basically 1064 nanometer light, infrared, near infrared light, using this setup. And this laser chassis is actually quite handy. It has a integrated water cooling system. It also has Peltier cooler models, thermoelectric lens temperature cooling systems integrated in it, and they still work. And this is the laser itself actually firing. So it's actually, most of the light you see here is actually not from the laser, but it's from the flash lamp itself. So it actually wastes a lot of power by a lot of the light actually not being used in the actual lasing process itself. And so this is one of the limitations of this technology. So we're trying to work around this. I was actually interested in using solar light, solar radiation focused on this laser setup, and I did this a few years later, 2018, when we had a heat wave, kind of a really kind of a excellent period of clear, bright, sunny weather in Ireland, and I had a setup where I basically had a Fresnel lens, which is basically a big sheet of plastic with kind of grooves etched in it, and this would focus the solar radiation, ambient solar radiation, on a laser rod, and with a output coupler I could measure the power. And this is basically the general schemata of this setup. And the solar radiation is broadband, of course. There's many different wavelengths in sunlight, but it also contains the pump level necessary to drive a 1064 nanometer laser, Neodymium Yag laser. And unlike the xenon flash lamp source, it requires no power. It just requires sunlight to drive itself. And I'm interested in this technology as a potential way in which you can not only create laser light using sunlight, but also potentially create it for driving chemical reactions. So here's the setup itself. It's actually a telescope mount. I mounted it on the same mount as that I use for my telescope. And the light is actually entering into the system via the Fresno Lens, and using this Newport basically infrared card, which fluoresces under under infrared light. I mean IR light, 1064 nanometer light. You can see it quite clearly here. It's actually forming a beam. It's forming a laser beam, which is made possible by focusing basically pure sunlight into the, here I am focusing it into the neodymium Yag crystal. So the crystal has no mirror structure. It's basically a one-way street as regards to the path of the light. So you can see here, focused more clearly, it's actually generating quite a bright laser. And the laser is possible to focus in a narrow beam at a certain distance of the card. And this is the whole setup itself. So this was an experiment that I was doing for a few years, trying to see how I could make it more efficient. And the Fresno Lens is basically just a big sheet of plastic with, as I mentioned, grooves. It's actually one of these sheets that you can use for magnifying paper if you're short-sighted. Here it is using an infrared protective filter just to eliminate some of the glare, so that you can see some of the actual infrared light itself. So this eliminates some of the glare from the visible spectrum, just to try and get a better grasp of the process that we are interested in. So at this wavelength, you're seeing infrared light in the roughly 800 to 1064 nanometer range. And the sunlight is being focused because the light emitted from the sun is not only visible but contains a significant portion of the near infrared, so you can focus it. And trying to make the system more efficient, so if I just pause the video here, you can see I have the a filter over the Fresnel lens. So this is actually a near infrared and near ultraviolet dual bandpass filter, Congo blue filter, basically the same type of filter that I use in my near infrared reflectance of plants. And what I'm trying to do here is eliminate the excess visible spectrum light, which causes unnecessary heating and unnecessary stress on the crystal, the neodymium Yag crystal. So it's to try and isolate as much as possible the laser, the sunlight, the band of the sunlight, which is responsible for producing the lasing effect in this crystal setup. So I'm focusing the light on the crystal using these basically pound shop, cheapo retort stands, and trying to focus the light into the beam setup. So I actually have a video. I tried to get in close and see the actual crystal itself. So the blue part here, that is actually the crystal, one of the facets, the front facets of the crystal. So yes, it is actually, even with a bit of cloud cover, it is actually producing laser light from this setup. And just moving along a little bit, the laser, however, does get warm, even with the unnecessary light being filtered. Using the filter, the excess laser light does cause the crystal to heat up, which is why the cooling system is necessary. Even in this setup, I haven't incorporated it in the trial of this system, but it is necessary because it actually gets quite significantly hot. And I did thermal infrared temperature testing of this setup. So this is actually without any light being shone on the laser crystal. So you can see ambient temperature roughly, because it's a black surface, it's absorbing a lot of ambient thermal infrared. So it's 32 Celsius. Again, this was during fairly heat wave-like temperatures in Ireland back in 2018. And I have other frames. So this is when the light is being focused on the crystal itself. So you can see it gets up to a temperature of about 92 Celsius. So quite hot. I mean, almost at boiling point range of water. So it's able to reach high temperatures, and so it needs to be cooled. And otherwise stresses will form on the crystal, it'll start to crack and so on. So yes, it's even at the front facet of the crystal, it's 81 Celsius. So using my FLIR, my thermal infrared camera, I was able to do some pretty basic diagnostics of the temperature range and the necessity, assessing the necessity for cooling of this laser setup. So why would anyone even want to build a solar-powered laser? What are the applications of this? There are two reasons, or many reasons, but the two I mentioned is to test their use for energy resource production on Earth, or investigate as a potential as a way to focus solar energy in space for use in space-based lasers for various applications. Power, communications, laser-based communications are something that is being actively explored, but also propulsion. Laser propulsion of spacecraft, solar sail spacecraft, is something which I'm interested in the case of how to propel, say, a graphene solar sail, something that is fairly temperature resistant. Graphene can be raised to very high temperatures, but it's also very light, so it can be propelled through space. So the test for the use as energy / resource production on Earth. What do I mean? Well, the main energy resource production which the system would be concerned with, a solar pumped energy laser system would be concerned with, is basically the reduction and oxidation cycles of metal oxides, because metal oxides some metals, and magnesium, for instance, magnesium being the most common one used in this cycle, can be reacted with water, seawater, salt water, and can produce hydrogen. And the salt water actually is a source for magnesium itself. And most magnesium, if you didn't know, is actually derived from salt water. Actually, it's a byproduct of desalination, but also of the refinement of salts extracted from salt water. So this can be then in turn reacted with salt water itself and produce hydrogen. So this is a kind of a circular, potential circular hydrogen economy. When it reacts with water, the metal becomes oxidized. It forms, say, magnesium, reacts with water, produces hydrogen, forms magnesium oxide. And it's this oxide which can be actually irradiated, and you can do basically solar-assisted reduction. Basically laser-based reduction of a metal oxide. Now, laser-based reduction is actually something which is, quite commonly used. For example, graphene oxide can be reduced to graphene again by an infrared laser. And this technique isn't new. There's actually been developments of this over years. So there is for example, like using magnesium in an electrolyte to produce electricity, or a magnesium film in a kind of an old, like the old basically magnetic reel of tape, going through a reaction chamber and generating electricity. And this system has potential for being recycled, basically recyclable. And the whole technique of laser-based magnesium oxide reduction could be used as an energy cycle for with laser power derived from PV or wind energy. And there is actually this, again, as I mentioned, is not a new technique, not a new technology in Uzbekistan. There's actually the largest solar furnace in the world, and it actually does precisely this at a much larger scale. It actually focuses sunlight into a basically a laser, solid state laser enclosure, and at one end the light is entering into the enclosure. The laser is cooled, but the resultant laser light is then focused onto a reaction chamber, which, among other things, can reduce and does reduce magnesium oxide to elemental magnesium. And the elemental magnesium can be used for energy production potentially, or generally used as a way in which you can actually get elemental magnesium recycled from magnesium oxide. So it can essentially drive chemical reactions. So this is called the solar furnace in Uzbekistan, and you can look this up. It's quite an impressive structure, and it's currently the largest one in the world. So this is definitely a potential energy source worth exploring, in my opinion, not only because of the potential for energy production on Earth, but also energy production in space. So you could imagine space or the orbiting of the Earth perhaps would offer even superior ways in which one could actually generate laser light. Now, the laser light would have to be focused on an offshore facility, but this could perhaps be a side benefit, a kind of a positive coincidence, because, as I mentioned, magnesium can be derived from salt water. So you could imagine a country with, say, a desalination facility on an offshore rig or offshore barge or whatever, or an offshore facility, just like an oil rig, basically, desalinating seawater, using the fresh water for maybe domestic consumption, perhaps other resources, but also you could derive the magnesium from the salt. The excess brine would produce salt water, and would then produce crystalline salts, would then be a source of magnesium oxide, which could then be irradiated by a space-based laser, which could then generate not only elemental magnesium, but then hydrogen. And then the elemental magnesium would go into a fuel cycle by reacting with, lo and behold, seawater, which would be in abundance all around this facility, this theoretical facility. And this would be a hydrogen, basically, well. This would be a hydrogen factory, in effect. So you could pump hydrogen effectively offshore and produce it in situ. So this is a very interesting potential energy source. Again, unfortunately, not being investigated with any real gusto, it seems. So this is just a general other types of solid state lasers, not only neodymium YAG but also erbium YAG, which can do the same effect. And of course, they're subject to, as I mentioned, heat, different types of heat loss that has to be exploited to cool down the lasers, and so on. And that's part one of the applications. Part two would be, of course, for a laser-based propulsion system for space-based applications, or for launching drones, potentially satellites, who knows. So it could be a potential launch mechanism as well. This is something that has been explored on and off, again with limited results. Some of this cartoon depicts an experiment which happened on and off over the years in a facility, which used basically basically like cone-shaped craft and propelling them using pulse laser systems, and it did work. but it had limited efficacy, primarily because of the laser focusing ability. However, this was perhaps a victim of the fact that it was being done on the Earth's surface, whereby scattering of the light obviously occurs. But in space, we have no such difficulty. Lasers travel without dissipating through space because it's a vacuum, and this is one area of interest for space-based propulsion using solar sails that could be assisted with perhaps particle beams and photon particle self-guiding, other techniques such as that. And this is really perhaps the only way in which one could get interstellar space probes, spacecraft out of the solar system in a controlled fashion without using gravity assists and so forth. So it's definitely an interesting topic. It's one explored obviously in science fiction, but is technically possible using space-based lasers, perhaps of the type that I describe. And of course, they're able to, the advantage being that they're able to achieve velocities, fractions of the speed of light, which make interstellar space travel a possibility using this technology. Again, this is all speculative, but it's speculative within, I suppose, not too far-fetched realms of physics and engineering. So, thank you for watching. This was a kind of a summary of a video that I'd done in the past, combined with new results, and I actually hope to do more experiments like this again in the future. So thanks for watching, and have a good one.